We're back. I realized that my video had timed out, so we're going to take page 2, take 2. All right, so note number 2 says the discrete values have to be transferred or become continuous values, okay? And your textbook will talk about that. Okay, so your textbook will talk about that more thoroughly, just as we're going to talk about it. But what I'm suggesting is that you also read the textbook pages that have been uploaded from yesterday to get more than one introduction to this idea, okay? So since the normal distribution uses continuous values, i.e. decimals, the k value is converted to a decimal value, okay? So this idea of the discrete value becoming a continuous value is what we're going to talk about in these examples. Okay, so for example, if p is at least 15, let's see if we can do this on a number line here. Okay, so there's our 15, 16, and 14. Okay. If p is at least 15, right, it means that the probability of k being 15 is like this, right? It's all of these values, all right? Because we're taking our exact number of successes being whole numbers and we have to convert them to decimals because we're using a normal curve which uses decimals. Okay. But the rule is that we have to be a value for k, or in this case, x. So this is simultaneously x is representing k, successes, okay? We have to be outside of this shaded area. So for our purposes then, in this example, okay, x would have to be 14.5 because that value would round up to 15 and therefore be included, okay, in this phrase at least 15. All right, if the probability is more than 10, okay, it's not 10, right? More than 10. So number line here, okay? So if it's more than 10, it would have to be somewhere over here. Right? It would have to be greater than 10. Now, for our purposes, we understand that our k successes is decimals, right? So our k successes is whole numbers. Okay, so technically we would say, well, k is 11 or 12 or 13 or 14, etc. Okay, but because we're talking about converting this whole idea to approximating probability with a normal curve, we have to be outside of this value, which is an x value of 10.5. Okay, and that would be the value of x when we calculate the z-score. This is going to be completely related to page 312 in number 7b. Okay, so that's really a part of the question you're going to need to know for 7b. If the probability is no more than 5, okay, so it's no more than 5, that means that the max is 5 and less, right? Okay, so there's 5, 4, 6. Okay, so if it's no more than 5, we've got this, right? We've got 5, and we've got 4, and we've got all the values to the left of that. Okay, but now what is outside of this band of values? Well, it's x is equal to 5.5. It's got to be outside of. Now, some people might say, well, I can't round 5.5 down to 5 that doesn't follow the rounding rules, and I realize it's asking you to suspend your rounding rules, the ones that you've known since elementary school. I understand that, but it's always going to be an x value that is outside of the k successes. Okay, so outside meaning that this is right to the, if the values for k go down in the number line, then you're going up by a half. If your values are going up, then your k value or your x value is down by a half. Okay, so what we're trying to do is say what x value as a decimal would include all the values that's stipulated here, but bearing in mind or remembering that your x value has to be a decimal, and it's always going to be 0.5 of something. 0.5 of something. If the probability is less than 5, so less than 5 means not including 5. Okay, what does that mean? Okay, so there's 5, there's 6, there's 4. Okay, so less than 5 would be 4, 3, 2, 1, etc. Okay, so we'd have to be outside of this number line. Oops, yeah, okay. So outside of this number line, well then that would be that x would have to be equal to 4.5. Okay, so it's always if the number line is going to the left, the shaded area is going to the left, then you have to add 0.5 to the specified value. If your number line shading is going to the right, then you have to, there's not a really good rule for that one. Okay, so in other words, here's the rule. It always has to be outside of the value that you're being asked to find. Okay, so it's outside by 0.5. Okay, so that last example refers to number 7C in your textbook. All right. Example 2. A card is drawn from a standard deck and replaced. Now this part that's being replaced is just like the Bernoulli trials. Okay, where the Bernoulli trial says that each probability is unchanged. Okay, from trial to trial, the trials are independent. It means the probabilities are not changing. So that's two ways of saying the same thing. All right, the probabilities are unchanged from trial to trial, which means that each trial is independent of one another. Okay, it doesn't influence each other. Okay, so therefore, we're going to use the n choose k times p to the power of k, 1 minus p to the power of n minus k. Now, we're going to use this when n is fairly small, okay, fairly small. I'm going to put that in quotations, right? And k is, again, small and not at least. Okay, not at least. All right. So if n is the 40 times, which is the total number of trials, consider then what's the probability of getting exactly 10 cards that are diamonds. So that's our k successes. We want 10 successful withdrawals of cards that are specifically diamonds. So we're going to use the probability that the discrete random variable takes on a value of 10 using the formula of n choose k times p to the power of k times 1 minus p to the power of n minus k. All right, so we're going to sub in an n value of 40 trials, a k value of 10. Now, we do not need to use a decimal value. There's no decimal values when we're using Bernoulli trials, okay? So there's no k is decimal. If we're using a Bernoulli trial, if we're using this formula, no k is decimal. So specifically k is 10, and then the probability now is the probability of getting a card that is a diamond. Okay, so the probability of a diamond in a regular deck, because there are 13 diamonds in a regular deck, out of the 52 card total. Okay, that's our probability. Now, we should be able to reduce the fraction to 1/4, which hopefully makes sense to you. So k is 10, n is 40, and the probability we already said is 1/4. Alrighty. Let's sub this in. Okay, so we have n, where n is 40, k is 10, times the probability of 1/4 to the power of k, which is 10, times 1 minus 1/4, and n minus k is 40 minus 10. Okay, so this is a combination that if the numbers were smaller, we could look up Pascal's triangle, but we can't, so now we convert the combination to its formula. So 40 factorial divided by 40 minus 10 factorial times 10 factorial times 1/4 to the power of 10, and 1 minus 1/4 is 3/4, because you're taking a whole minus a quarter to the power of 30. Okay, so let's evaluate what 40 factorial divided by 30 factorial, 10 factorial, and then 1/4 to the power of 10, and 3/4 to the 30. Okay. Multiple steps here are being shown because you're going to have to use that in your Unit 5 video assessment. Alright, so 40 factorial divided by 30 factorial divided by 10 factorial. Let's do it over here. So 40 factorial divided by 30 factorial. Okay, so these are just standard numbers converted to a standard notation, scientific notation we should call it. So it's that number times 10 to the power of 32. Okay, so it's used when the number is super small, and then divided by 10 factorial is equal to 8, 4, 7, 6, 6, 0, 5, 2, 8 times 1/4 to the 10. So bracket 1 divided by 4, bracket, converts that to a decimal for me, and then y to the x, or x to the y, depending on your calculator button, to the 10. Very small number. Still have to use it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 9, 5, 3, and then bracket 3 to the 4, bracket, and then y to the x, which is 30. A little bit larger of a number, 0.123, 1, 2, 3 zeros, 1, 7, 8, 5, 8, 2. I leave that number on my screen, times 0 decimal 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 9, 5, 3, times this very large number, 8, 4, 7, 6, 6, 0, 5, 2, 8. 0 decimal 1, 4, 4, 2, 6, 2, 2, 7. Okay, so that's the probability of selecting 10 diamonds. Okay. Alrighty. So no more than 4 cards are diamonds. Alright. So no more than 4 cards. Okay, so no more than 4 are diamonds. Alright. So if I want to know what's the probability that no more than 4 cards are diamonds, I have to consider all of these values. K is 3, K is 2, K is 1, K is 0. That means I have to have 1, 2, 3, 4 formulas for the Bernoulli trial. That means I have a lot of formulas. Now, I can certainly do that if I wanted to, or I could try the normal distribution, okay? Let's try the normal distribution. If you want to do the formula, you can definitely do that. Okay, so if I want no more than 4 cards of diamonds, I have to use all of this, okay? But because outside of the value of the K successes is X equals 3.5, I have to deem that K, in this case, is 3.5 and less than that, okay? So I'm going to use, to avoid, actually I'm going to put this, to avoid the use of the above formula, 1, 2, 3, 4, 4 times, we'll use the normal distribution. Okay? All right, so we have to first check symmetry. Okay, so is there symmetry here? Well, let's see. So n times p is greater than 5, so we're going to sub in the n value of 40, and the probability is still diamonds so it's still 1 over 4. Okay, so n times p, n is 40, times p, which is 1/4. 40 of, or 1/4 of 40 is 10, so which is greater than 5, so that's good. And then symmetry will dry this one, so b is n times, and you get these from over here, right? So symmetry, so a and b, that's my first check. Okay, so n times 1 minus p has to be greater than 5. So n bracket 1 minus p, what does that equal to? Well, we're going to sub in the n value of 40, and we're going to still sub in the p value of 1/4. So we're going to have 40 times 1 minus 1/4. So 40 times 1 minus 1/4 is 3/4. If I take 3/4 of 40, that should be 30, but we can check. 40 times 3 divided by 4 is 30, which is greater than 5. Okay, so that's a check there. Okay, so therefore the probability is symmetrical. Now we're going to go to step 2. And I'm going to do it right here. All right, so step 2 for example 2b is using the formula of z equals x minus the average divided by the standard deviation, where we're going to sub in the x value, which is k successes. So that in this case is 3.5, okay, because it has to be a value that includes the decimals. The mean is still, again, remember, might want to highlight these. Okay, so that's step 1. And then step 2. Okay, so where x is this, and sigma is that, right? So this is step 2. All right. So n times p is n, where n was 40, and p is still a quarter. And so the mean is 10. And if you say, well, we've already found that over here, then that's completely fine. You can just sub that in right away. So x is 3.5. The average is 10. What else do we need? We need the sigma. Okay, so you're still doing n times p, 1 minus, right? N times p, 1 minus p under the square root. N times p, 1 minus p, all under the square root. So we're subbing in the n value, which is still here, 40. We're subbing in the probability that is still up here of 1/4. And then we're going 1 minus 1/4. So we've got 40 times a quarter times 3/4. Okay, so those are being multiplied. If you want, you can multiply them all together. So 40, move it over here, 40 times 1 times 3 equal to, divided by 1 times 4 times 4, which is 16. Okay, which is 7.5. Okay, if you want, you can do it the following way. You can write 40 times 1 times 3 is 120. And 1 times 4 times 4 is 16. And then you can go 120 divided by 16. Okay? We want the square root of that. 2.738. 738. Use 3 decimal places. Okay, so that is our sigma. All right, so z is equal to x, where x is 3.5, minus the mean, which is 10, all divided by 2.738. 3.5 minus 10 is equal to negative 6.5 over 2.738